In this brief introductory video, I'll explain how to use the Asteroid Institute's bulk ephemeris service to predict the on-sky position of orbiting bodies. This service is built for survey planners, follow-up observers, and anyone doing observability work who wants ephemerides backed by an open-source pipeline. To access Atom Ephemeris, go to b612.ai, log into your Atom account, and then click on Ephemeris in the sidebar. To start a new job, click this button. This form has two steps. First, you pick the orbits that you care about, and then you pick the observers and the times. For orbits, you have two input modes. Named source lets you look up known objects by name or designation against JPL's Small Bodies database, JPL Scout for recently discovered NEO candidates, or ESA's NEO-CC catalog. You type in one or more designation, hit validate, and you'll see a green check on each successfully resolved object. So here, let's just try 2024 YR4 and Apophis for good measure. So that's the first method. We also allow you to supply a CSV or Parquet file of orbital elements in Cartesian and Keplerian or cometary formats. A sample CSV is linked right in the form so that you can match the schema. We do recommend our Parquet format, which uses the orbits model in our open source Atom core package. You can view that on our GitHub. But we'll go with the named source route for now. For observers, you have three modes. Inline is one row per observation point. Great for a handful of upcoming nights at specific sites. Pick an observer code, set a date, add another row. So here we'll do X05, 0101, 2026, first thing in the morning, and we can add another row, and it'll prompt you to go with one that was already added. And now we have two dates. Time grid is the bulk mode with the time step cadence. You pick a list of observer codes and a start and end time, and the service evaluates every observer at every step across that window. This is the typical setup for survey planning or finding charts over weeks or months. Note that we limit the range to the date ranges available for the most restrictive observer in the list. So for example, space telescope observers have limited time ranges in which they're able to operate. So now let's go with, say, X05 again, and I41, ZTF. So here we specify, you can either do this in MGD or in calendar date, and again we'll do 01/01/2025, say, and 01/01/2026, with a 1 day step. And now you'll see here that that shows the number of output rows that we expect to have. Finally, we have a file upload option. And this allows you to upload a CSV of explicit code and time pairs for cases where your observation plan is already laid out elsewhere. You can also provide an Atom Core Observers Parquet file, which again is our recommended approach. Now, one note on observer locations. You have the entire Minor Planet Center catalog of ground-based sites, searchable by code or name, and 3 space telescopes, James Webb, Hubble, and TESS, computed from their up-to-date SPICE kernels. The form knows each spacecraft's available kernel coverage window. If you ask for James Webb in 1990 or Hubble in 2030, you'll get an error before submit, so be wary when setting up your observers file. In this last section, you pick your output formats: CSV, Parquet, ADIS PSV, or any combination. You can also choose whether or not you would like magnitude predictions at each ephemeris point. This will work if you got your orbit from SBDB, which provides an H magnitude, or supplied your orbits as an Atom Core Parquet file with physical parameters defined. We'll select all of those for now. And finally, hit submit. So on submission, you'll be taken to a results page that shows your job parameters and live status. The job runs on our cluster. You can close the browser and come back via the link on your job list. Most runs finish in well under a minute. The large grids over long time ranges can take longer, or if we have to spin up a new node in order to run your job. And now we'll switch over to a job which is already completed. Great. Now I've jumped over to a job which is already completed. Once the job completes, this page populates with the full result view. And note these inputs are slightly different than the one that we ran previously. At the top of the page is a result summary: the orbit count, the observer count, total ephemeris rows. Below that is the light curve chart. Each trace is one object as seen from one observer with predicted V magnitude over time. One detail worth knowing, rows where the target sits within 5 degrees of the Sun are rendered as gaps. Our photometric model can't really be trusted near conjunction, so we mask those points in the chart only. The downloaded data are untouched, though you should be aware that because of assumptions made, we can't really predict magnitude that well at these degeneracies. Below the chart is a paginated data preview. The first rows of the CSV with column descriptions for every field: sky position, RA and deck rates of motion, solar elongation, moon separation, altitude and azimuth were applicable, predicted magnitude, light time, and 1 sigma position uncertainties when covariance was provided on the input. Then we have download buttons: Parquet, CSV, ADIS PSV, the IAU pipe separated format. There's also a download input orbits button. This gives you the resolved orbits as a Parquet file, exactly the state vectors that were fed into the propagator. This is useful for reproducibility, for rerunning with the same starting orbits weeks later, or for inspecting what SPDB or NeoCC actually returned for your designations. Finally, there are 2 more affordances on the result page. There's a sharing option, in case you want to create a link that anyone can look at in a read-only mode, handy for sending results to a collaborator who isn't on the platform. And finally, there's the Modify Inputs button. This will take you back to the form with every field pre-filled from this run. You can tweak the time range, add an observer, change the output formats, and submit again. Much faster than retyping. I should note, everything in this UI is also available through the Atom REST API, and the underlying machinery, assist propagation, the Ephemeris schema, ADIS output, it's all in our open source Atom core library on GitHub and on PyPy. For the REST API documentation, you can click on the API docs on the side. And note that for many of these, you'll have to generate an API token. Finally, if you're interested in viewing more of our open source projects, you can get to those from the public site in open source and viewing all of our projects on GitHub. Thank you for taking the time. If you've got any use cases that aren't covered here, larger scales, custom observers, or additional output formats, please hit the contact link and shoot us an email. Thanks so much.